Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory undergraduate combinatorics based on my book, An Invitation to Combinatorics. This lecture is about counting subsets or combinations and binomial coefficients. S and T are going to be non-negative integers with S less than or equal to T. And bracket T is going to be the set that consists of 1, 2, 3, 4, all the way till T. And it's our stand-in for a set with T elements. Often, we just care that it's a set with T elements. It could be a set of your favorite teddy bears, but it's a set with T elements. Bracket 0 stands for the empty set. An S subset or an S combination is just a subset of size S of bracket T. You have T elements. What are the subsets of size S of them? Those are called an S combination, an S subset. You're selecting S of the T elements of bracket T, and it's an unordered selection. So it doesn't matter what order you pick them, you're picking S of them. That's all that matters. One way to think about that is that you have a room full of T people, and you want to make a committee of size S. Each way that you make a committee of size S is an S combination or a subset of size S of that collection. Now, bracket T choose S, that's how we read this bracket T choose S, is the set of all subsets of size S, the set of all these S combinations of bracket T. And T choose S, so which is just a T with an S underneath it and two parentheses, is the number of those. So T choose S is a number. Bracket T choose S is a collection of subsets, all subsets of size S. This T choose S is called a binomial coefficient. In this lecture, I will not get to telling you why it's called a binomial coefficient. It has to do with the binomial theorem, expanding x plus y to the n. In a future lecture, I will. Let's look at an example. Bracket 4, 1, 2, 3, 4, a set with 4 elements. What are its subsets of size 2? So that's bracket 4, choose 2, and it's a set of sets. One element in it is 1, 2. 1, 2 is a subset of size 2 of 1, 2, 3, 4. 1, 3 is another, 2, 3 is another, 1, 4, 2, 4, and 3, 4. Those are all the subsets of size 2 of 1, 2, 3, 4. Bracket 4 choose 2 is a set of sets. Since we don't like to keep saying set of sets, we often say it's a family of sets, but a family of sets just means a set of sets. And 4 choose 2 is how many subsets of size 2 does a 4-element set have? And the answer is 6, because there's 6 subsets of size 2 in a set with 4 elements. Let's do a few more examples. Bracket 0 is the empty set. So what is 0 choose 0? Well, it's 1, because the set with 0 elements, which is the empty set, has only one subset of size 0. Every set of size n has only one subset of size 0, and that's the empty set. So n choose 0 is 1, as long as n is a non-negative integer. In fact, n choose n is also 1. What does that mean? You have a set with n elements, and you want to find a subset of size n. You want a committee of the whole. You have n people, you want everybody. How many ways can you do that? Just one way. And choose 1, what is that? That means you have a set of size n, and you want committees of size 1. How many ways can you do that? Well, a subset of size 1 could be just 1, or just 2, or just 3, and all the way just n, so there's n of them. So n choose 1 is n. What I want to do now is to give you a formula for these binomial coefficients. This is a formula you might be familiar with from high school, but I want to prove it, and the argument is actually quite interesting. So S is a non-negative integer, as is T, and S is less than or equal to T. And I want to tell you a formula for T choose S. By the way, T choose S, there's other notations for it also. T with a capital C S is another notation for combinations. I'm going to tell you what this T choose S is, but I'm going to prove the result before writing the statement, because the result comes from the proof. So I'm going to start with a set with T elements. T choose S is the number of S combinations, the number of subsets of size S of this set with T elements. That's what I want to count. But I'm going to take a detour. I'm not going to count that. I'm going to ask how many S permutations does bracket T have? Now, what's an S permutation? That was a subject of a previous video. It's an ordered list of S elements. I want S elements just like when I want to find a S subset, but this time I also want to order them. The answer is not that complicated. If you have S slots that you are going to put elements of bracket T in, for the first slot, you have T choices. You can put any of 1 through T in that first slot. Regardless of what you put in the first slot, you have T minus 1 choices for the second slot. Regardless of your choices for the first and second slot, you have T minus 2 choices for the next one, and so forth. And so the answer is going to be T times T minus 1 times T minus 2. You go so that you have S terms because you have S spots. That's a truncated factorial. The notation I use for that is T in parentheses with an S at bottom. We call that a falling factorial, or you can think of it as a truncated factorial. It starts with T and goes down T times T minus 1, T minus 2, like a factorial would. You stopped after S terms. The first one is T minus 0. The second one is T minus 1. The 47th one is T minus 46. It's one less. And so the S one is T minus S minus 1, which is T minus S plus 1. This is what the answer is to that question. We can write this in terms of factorials if you like. We are wishing that this actually would go all the way down and give us a T factorial. But if we write it as T factorial, then we've added some extra terms that we don't need, and we need to divide by those. The terms that we need to make it T factorial is exactly T minus S factorial, because it's T minus S times T minus S minus 1 times T minus S minus 2 all the way to 1, and that's T minus S factorial. So we answered that question about S permutations. But what I'm going to do is that I'm going to answer this question yet again. That's not the question that I really want to answer. But by answering in two different ways, I will have two answers that will have to be the same. The way I'm going to do it the second time is I'm going to say, don't just start putting elements in your S permutation, but first decide which of those T elements you're going to put there. You're only going to put S of them. You're not going to put all of them in that permutation. Pick the ones that you want first. So you have T elements. You've got to choose S of them. How many ways can you do that? The answer to that is T choose S. We don't have a formula for it, but whatever it is T choose S. Well, after I've chosen them, I haven't ordered them yet. So then what I have to do is I have to permute them, find all their different ways that I can permute them. And if you have S things, just the same argument as before, you have S choices for that first spot, S minus 1 choices for the second, all the way till 1. So it's S factorial. S things have S factorial permutation. So T choose S times S factorial is also the answer to the question, how many S permutations does bracket T have? You can have it as T factorial over T minus S factorial, T choose S times S factorial. These two answers must be the same. But if they are the same, then you can solve for T choose S. This is our roundabout way for finding T choose S. So we divide by S factorial, and we get that T choose S is T factorial over S factorial times T minus S factorial. So now we have our result. T choose S is T factorial over S factorial times T minus S factorial. A lot of times in introductory combinatorics, we can think of counting problems as balls and boxes. You have balls that you want to put in boxes, and you have certain conditions on the balls, the boxes, and the capacity of the boxes. S and T are integers with S less than or equal to T. Let's say that you have S identical balls, balls that you can't tell apart. They're all the same. But you have T distinct boxes. Maybe they have a number on them. And you want to place the balls into the boxes, but you have a condition. You don't want any box to get more than one ball. Now, some boxes are going to be empty because S could well be less than T. How many ways can you place S identical balls into T distinct boxes in a way that each box gets at most one ball? And the answer is, if you place the balls in the boxes, all you've done is you're choosing which boxes to put the balls in, because you can't put two balls in the same box. What you're doing is that you're picking S of the T boxes to put the balls in. So the answer is T choose S. So T choose S counts the number of ways of placing S identical balls in T distinct boxes in such a way that no box gets more than one ball. Let's do some examples. A standard deck of cards has 52 cards, and 12 of them are picture cards, king, queen, or jack. There's 4 of each of those. 3 times 4, there's 12 of them. There are 4 players, and you're going to give each of them 13 cards. What's the probability that every one of them gets exactly 3 picture cards? So you're distributing all the cards, so the picture cards are going to go somewhere. I want to know what's the chances of every one of the 4 players has 3 picture cards. Probability questions, as long as there's finite sample spaces, finite number of possibilities, it's really a counting question. The probability in a finite case, when all the different cases are equally likely, is given by a fraction. In the denominator, in the bottom, you write the total number of possibilities, total number of ways that you could distribute these cards among the players. On the top, you put the number of the desired outcomes. In this case, the number of ways that you could distribute the cards, and each player gets exactly 3 picture cards. So let's look at the total number of possibilities first. How am I going to distribute these cards? Well, the first player is going to get 13 of the 52. How many ways can I give 13 cards out of 52? That's 52, choose 13. You have 52 cards, pick 13 of them, give it to the first player. There's 52, choose 13 ways. You're left with fewer cards. You have 39 cards, and you're going to give 13 of them to the second player. How many ways can you choose? 13 cards out of 39 to give to the second player is 39, choose 13. Now, for the third player, you're left with 26 cards, and you're going to give 13 of them. So 26, choose 13 is how many ways you can do that. And for the last player, 13, choose 13. You have to choose all 13 out of the 13. Those choices are independent of each other. Regardless of which cards you give to the first player, you still have 39, choose 13 choices for the second player, and so on. You multiply these. This gives you the total number of possibilities. It's not a good idea to write these numbers and multiply them. You get a very humongous number. When you divide, a lot of those factorials cancel and life gets easier. Now, the desired outcomes. Desired outcomes are we're making sure that every person gets 3 picture cards. So we go to the first player. We first decide to give him the 3 picture cards. And for that, we have 12, choose 3 choices. Now, out of the other ones, the cards that are not picture cards, we've got to give this guy another 10 cards. So there's 40 non-picture cards. We have to choose 10 of them to give him. And the number of ways of doing that is 40, choose 10. Now we go to the second player. Again, we first give them a picture card. And the number of ways of doing that is 9, choose 3, because we've already given 3 of the picture cards. And then we give him a non-picture card. We've already given 10 of the 40, so we have 30 left, and we have to pick 10 of those. For the second player, the total number of ways that we can give them cards so that they get exactly 3 picture cards is 9, choose 3 times 30, choose 10. And we're multiplying these. Now we go to the third player, do the same thing. 6 picture card lefts, choose 3 of them. 20 non-picture card lefts, choose 10 of them. And then for the last player, we really do not have any choice because we're picking 3 out of 3 and then 10 out of 10. So that's the desired outcomes. We divide these two numbers. The desired probability is going to be these two products of binomial coefficients divided. If you write our formula, a lot of the factorials cancel and you get about a 3% chance. Another example, you have 8 friends and you want to split them into pairs. Maybe you want to work on some tasks or be teammates for some kind of a game. So you want to split the friends into pairs. In how many ways can this be done? You could try counting this yourself. You should always stop the video, try to do the problem yourself, then come back to the video after you get stuck and you don't know what to do. And in fact, after you get stuck, the best thing to do is leave it alone for a while and then go back to it. But if you want, you can go back to the video. That's the easy way out, but not the best way to learn stuff. We're going to say that n is going to be the number of ways to pair up the 8 friends. M is also going to be the number of ways to pair up the 8 friends, but also assign them to a distinct task. M is going to be a little bit different than N. N is the thing we want. How many ways can you pair up the 8 friends? M is going to be, you're going to pair them up, but you're going to give each one of them a different task. The first pair are going to mow the lawn. The second pair are going to wash the dishes. The third pair is going to take the trash out. And the fourth pair is going to watch TV. So you have specific tasks that you're going to give to each of the pairs. These two numbers are not going to be quite the same because in the first one, you're just pairing them. You haven't decided yet what task they're going to do, or maybe they all have the same task. It doesn't really matter. You're just pairing them. But M, you're giving them each a distinct task. What's the difference between M and N? If I knew N, then I could find M. After pairing up, I could say, which pair is going to do task 1? Well, I have 4 choices for that. Which pair is going to do task 2? I have 3 choices now. Which pair is going to do task 3? I have 2 choices and 1 choice. I get n times 4 times 3 times 2 times 1. So first I pair people up into 4 groups. Then I will assign the groups to the tasks. So n, the number we want, is actually m divided by 4 factorial. Now, how am I going to find m? Let's think of the first task. I have 8 people. How am I going to pick 2 people to do that first task? Well, the answer is 8 choose 2. I have 8 people. I've got to pick 2 of them to do that first task. 8 choose 2 choices. But then I've got to do the second task. Out of the other 6 people, I pick 2 people to do the second task. So I have 6 choose 2 and then 4 choose 2 for the third task. And for the last task, the remaining 2 will have to do it. And that's 2 choose 2. So I've got a formula for m, and that's 8 factorial over 2 factorial, 6 factorial from our formula for binomial coefficients. The second one is 6 factorial over 2 factorial over 4 factorial, and so on. You notice that the 6 factorials cancel. The 4 factorials cancel. These 2 factorials, remember, those are just 2. So it's 8 factorial over 2 factorial to the 4th, or 2 to the 4th. But m wasn't what I wanted. N was what I wanted. So I have to divide that by 4 factorial. And if you calculate that, you get 105. That's the answer. Like any other combinatorics problem, there's multitude of ways of doing that. This problem, you could have done it actually simpler. I could have said, I have 8 friends and I want to put them in pairs. I will pick the tallest person in the group. And I say, okay, I'm going to give you a partner. How many ways can I do that? Where there's 7 other people, so I have 7 choices. Those are paired, go away. Then the next tallest among the remaining people. So you come up. That's a specific person. There's no choice. I just picked the tallest among the remaining people. There was 6 remaining. I picked one of them. There's 5 left. I picked one of those to make the partner of this one. So far, 7 times 5. Now I again from the remaining 4, say the tallest one come forward, and I give them a partner, and I have 3 choices. And at the end, I have 2 people left, and they got to be partners. So the answer is 7 times 5 times 3 is 105. So that was slightly simpler. But the point here was to show you how you use binomial coefficients. Here's another somewhat different problem. This is a lattice path. I have a 9 by 7 grid, 9 in this direction and 7 vertically going up. And I'm looking for northeast paths. You're always on the grid lines. If you're at this corner, you have 2 choices. You can go up or you can go to the right. That's the only things you can do. What I want is the number of these kinds of northeast paths from 0, 0 to 9, 7, but I also have 2 conditions. I want to make sure that I go through 2, 3. That's my favorite spot. I want to make sure I go through there. And I want to miss 4, 6. I want to avoid 4, 6. So I want to know how many northeast paths, the paths that go either right or up along the grid lines from the origin 0, 0 to 9, 7, but making sure that they go to 2, 3, but miss 4, 6. So the first question I'm going to ask is that how many paths are there from 0, 0 to 2, 3? Because I've got to go to 2, 3 because that was one of my conditions. So might as well actually figure out how many ways can I get from the origin to 2, 3. Now, if you go from the origin to 2, 3, no matter how you do it, you've got to take 5 steps. For example, if you take this path, you go up, over, up, over, up. There are 5 steps. Here's another one. You go up, up, over, up, or north, north, east, east, north. Again, 5 steps. No matter how you do it, there's going to be 2 horizontal steps and 3 vertical ones. The only thing you really have to do is decide when the horizontal steps are going to happen. For example, in this example, you have step 1, step 2, step 3, step 4, step 5. Each of these is either north or east. The horizontal step, the east steps, you have to pick where they are in that sequence. In this case, they're in step 2 and step 4. And in this other one, the horizontal ones are step 3 and step 4. So how many ways can you choose 2 horizontal steps? Decide out of those 5 steps, which 2 of them are going to be horizontal? You have 5, choose 2, which is 10 choices. So let's record that. There's 10 paths from 0, 0 to 2, 3. Now, how many paths from 2, 3 to 9, 7? Forget 4, 6 for now. Just how many paths from 2, 3 to 9, 7? Again, same thing. How many total steps we have? We have 11 steps. We have 7 horizontal steps and 4 vertical steps. Here's an example of such a path. I'm going to pick the vertical steps. Where's those 4 vertical steps going to come? In the example here, the first vertical step is in the 2nd step, then the 5th step, then the 7th step, and the last step. You have to pick 4 out of those 11 steps. And how many ways can you do that? Is 11 choice 4, which if you use our formula is 330. There's 330 paths from 2, 3 to 9, 7. But going from 2, 3 to 9, 7, I can't use all the paths because some of them actually go through 4, 6. And that was a place that I was supposed to avoid. I have to figure out how many of those are there to subtract from 330 because I can't use them. How many paths go from 2, 3 to 9, 7, go through 4, 6? That's the same as the thing we just did. You first go from 2, 3 to 4, 6. And for that, you have 5, choose 2 ways. And then from 4, 6 to 9, 7, you have a total of 6 steps. And you have to pick one of them to be the vertical one. And so the total number of paths from 2, 3 to 9, 7 that go through 4, 6 is 60. Let's record that also. So what's our final answer? The final answer is going to be 2,700. I took 10 and multiplied it by 270, which is the number of ways of going from 2, 3 to 9, 7, but avoiding 4, 6. And so the final answer is 2,700. The binomial coefficients will be subject of a later video where we will go in much more detail, and some of what I'm about to say will be repeated there. But I want to whet your appetite by giving you 2 binomial identities on binomial coefficients, and say a few words about the triangle of binomial coefficients, and then we will be done. Take two non-negative integers with k less than or equal to n, and I claim that n choose k is always the same as n choose n minus k. I will give you 3 proofs because each of them will illustrate how you can use different combinatorial ideas to prove things. N choose k is counting the number of subsets of size k of a set with n elements, and n choose n minus k is counting the number of subsets of size n minus k. I give you a bijection between subsets of size k and subsets of size n minus k. For every one of them, match it with its complement. And the complement is a set of size n minus k. And that means there must be as many subsets of size k, which is n choose k, as there are subsets of size n minus k, which are n choose n minus k. So those two numbers have to be the same. The second proof is even more straightforward. We have a formula for n choose k. It's n factorial over k factorial times n minus k factorial. Well, what's the formula for n choose n minus k? Instead of k, we put n minus k. We get n factorial over n minus k factorial, and then k factorial. These two things are evidently the same, and so they must be equal. Proof 3 maybe is the more interesting one. Count the number of northeast paths, just like we did in the previous example, from 0, 0 to st. Again, you have a grid, s by t grid, and you're going along the grid lines, and you're only going north, up, east, right, and you want to know how many are there. There are s plus t steps you have to take, and you get s plus t choose s, because there's s horizontal steps you have to make out of those s plus t, and you have to pick which ones are the horizontal ones, and you have s plus t choose s choices. But you could just as well pick the vertical steps, and for that you have to pick t of them. So s plus t choose t is another way of counting the number of northeast paths from 0, 0 to st. These two numbers have to be the same. Now do a change of variable. Instead of t, put k. Instead of s, put n minus k. Then t plus s becomes n, and s plus t choose s becomes n choose n minus k, and s plus t choose t becomes n choose k. And so those two must be the same because they're both counting the same thing, the number of northeast paths from 0, 0 to st. This is something combinatorics love to do. Count the same thing twice, different ways, and get an identity. Here's another binomial identity, which is actually a really important one for generating these numbers. So k is a number between 1 and n. My claim is that n choose k is n minus 1 choose k plus n minus 1 choose k minus 1. We've seen recurrence relations before, and we can use this to generate small numbers of binomial coefficients as far as we would like. So why is this true? Why is n choose k the same as n minus 1 choose k plus n minus 1 choose k minus 1? We could use the formulas, but that's not elegant at all. So n choose k is the number of subsets of size k subsets of 1 through n. These subsets come into two varieties. They either contain n or they don't. N is that last guy in that set, and we're picking on it and saying that a subset either has it or doesn't. How many do not contain it? If you have a subset of size k and it doesn't contain n, then the way you made that was you took k elements out of the remaining n minus 1 elements. How many subsets of size k does a set with n minus 1 elements have? The answer is n minus 1 choose k. So those are the number of subsets that do not contain n. But what if they do contain n? If you have n in your subset, then what's the rest of it? The rest is k minus 1 elements out of the remaining n minus 1 elements. So you have to choose k minus 1 out of the remaining n minus 1 elements. How many ways can you do that? N minus 1 choose k minus 1. So they have to add up to the total number of subsets of size k in a set with n elements. And so we have n choose k equals n minus 1 choose k plus n minus 1 choose k minus 1. Using that relationship, that recurrence relationship, you can calculate many of these. And the customary way of doing it is writing them in a triangle. The rows are telling you the ends. So n equals 0 is the top row, then n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and so on. The k's are the columns, k equals 0, k equals 1, k equals 2, k equals 3, and so forth. In every row, k equals 0 is the first one, k equals 1 is the next one, and so forth. For example, if you pick at one of these things, this guy is in row 5, column 2. Remember, rows start with 0, columns start with 0. That's 5 choose 2. And how did I get that 10? I added the 2 above that because n choose k is n minus 1 choose k plus n minus 1 choose k minus 1. So 4 plus 6 gives me 10. This 10 plus 10 gives me 20. 10 plus 5 is giving me 15. Every 2 entries in the triangle, you add them and you get the one right below them. And again, this 5 choose 2 is the number of ways to choose 2 objects out of 5. Almost everyone calls this triangle Pascal's triangle. And that makes sense in some ways because Pascal wrote a book about it in the 17th century, where in somewhat modern ways proved the properties of the binomial coefficients. Pascal didn't call it Pascal's triangle. but 18th century French mathematicians started calling it Pascal's triangle. But that's almost a misnomer because this triangle was used all over the world hundreds of years before Pascal. In Iran, in China, in Northern Africa, in the wider Islamic world, in India, people were thinking about binomial coefficients, their properties, and in fact had the triangle. I tend to call it the Karaji-Jia triangle. The reason for that is there are two very nice triangles left from a long time ago. So this one is from the Soleimani library in Istanbul. It's the triangle that was constructed by Karaji. His thesis does not survive, but Al-Samwal in the mid-12th century wrote a very nice thesis that describes it. And this is a copy of that. Now, this is from early 14th century. The copy is. This actually was written in the 14th century, some 300 years before Pascal, and has that very nice triangle of binomial coefficients. Samuel, who wrote the book, written in the 12th century, does ascribe it to Karaji and explains that Karaji says that this is how you do this, and the construction is very nice. Here's another example from China. Again, the original is from 11th century, a little bit later than Karaji. The document we have that have this is in Cambridge University Library, is from the 14th century, again, quite a bit before Pascal. And it's not just like people knew this triangle, they were using it for extraction of roots, for doing all kinds of combinatorial things way before Pascal. So for that reason, because of these two nice triangles that we have, one from Karaji and one from Jia, I like to call this the Karaji-Jia triangle. And this is the end of this lecture. I will see you in the next one.